Hello, everybody. So now we're going to discuss the flow measurement devices, which is something we need a lot in our applications in fluid mechanics. And this is important because when we have any or design any process, then we need to make sure, or we design it based on a specific flow rate, whether it's gas or liquid flow rate. So it's important to make sure that the process is operating at the design flow rate. Otherwise, the efficiency of the process is not going to be as needed, whether it's just fluid flow or this goes to another unit that is like a separation reactor, whatever the unit that's coming next. So if the flow rate is not as designed, the process is not going to operate as designed as well. So this is important to ensure the process is working properly. It's important because we can tell if there is any leakage or any issue with the flow, so we can take the corrective action and do what is needed to restore the original condition. And it's also economically important because if there is any leakage, let's say, or difference in the value that we desire than the value that's actually taking place there, the flow rate that's taking place. This means a lot of difference in the cost or the money that we expect. So let's say if we have 0.02% error in the flow measurement in crude oil, for instance, then it means that 68 barrels per day of difference if it's just 0.02%. So this means a lot of money. So it's important to know how much flow is there, because this will cost a lot of money if it's not accurate. It's also important for open channels, if it's rivers or any canals, for irrigation, for other reasons. So we need to know also how to measure the flow of water. So the message that I want to deliver here is that the flow measurement devices are very crucial and important for any process that contains flowing fluid. Of course, this is like a very, very, very big topic, so we are not going to go through a lot of details here. I'm just going to cover here some different types of flow measurement devices. We can put them under different branches. The one that we will discuss is the obstruction methods, because they share the same concept. And we have the variable area meters. It's a rotameter. Rotameter is something that's used in labs usually, or small flow rates that you can measure with this rotameter. And there are other methods that are specific for different cases, or for specific fluids, or that are required for high accuracy measurements, to put it this way. So for the sake of time, there are a lot of details in the textbook, and I really encourage you to read the textbook if you're interested in these types. But the one that I will cover here is the obstruction method, and the reason I'm just focusing on the obstruction methods is that it relates to what we were discussing in the energy equation, which is Bernoulli equation, because it's mainly based on Bernoulli equation. There is one other, by the way, device that's pitot tube. We already discussed it before. But pitot tube doesn't measure the flow rate. It measures the velocity at specific radius. And we can use pitot tube to measure the flow rate, and maybe we can discuss it after we finish the obstruction methods. So the obstruction methods flow meters are based on very, very simple theory, that we have a fluid flowing in a pipe, and we want to measure the volumetric flow rate of this fluid. So we know from Bernoulli equation that a fluid flowing in a pipe with a specific diameter will increase the velocity if the diameter decreases. the velocity of the fluid will increase if the diameter decreases, and which means that the kinetic energy increases, which leads to a pressure drop. And this is simply what we do, that we have a fluid flowing, and we intentionally reduce the flow. And this is why we call it obstruction method, that we obstruct the flow, we make it like going through a smaller cross-sectional area. So when the fluid flows through a smaller cross-sectional area, the velocity increases and the pressure decreases, and we can measure the pressure drop easily using a manometer or any other device. So we are not measuring the volumetric flow rate directly, we are measuring the pressure drop, and we will use the basics of fluid mechanics to measure or calculate the volumetric flow rate with the knowledge of the pressure drop. Okay, so this is the obstruction. The difference between the methods that the three different ways here, or the three different types of flow meters, is how we do this obstruction. This is only the difference, but they are all based on the same idea, that we reduce the cross-sectional area, and so the velocity increases. So we know that the velocity is not the same, and we have Bernoulli equation here. We have we will base our analysis assuming that there are no losses, which is not right, but we will fix this later. But this is important, that we base our assumption that there are no losses, there are no turbines, there are no pumps, and we assume alpha equals 1. So the equation would be the very famous first form of Bernoulli equation. It's not the modified Bernoulli, the basic Bernoulli equation. So the 2 points 1 and 2 are at the same height. The velocities are not the same, and the pressure is not the same, of course. So we can simplify the equation to be u2 square minus u1 square equals 2 delta p over rho. And delta p can be measured using the manometer, and we can also so this equation is not sufficient by itself, because we don't know the flow rate, so we don't know u1 or u2. But we can find the relation between these two. We know the right hand side. We fully know the right hand side, but we don't know the left hand side. So we need one more equation, which is the continuity equation, that the rho 1 a1 u1 equals rho 2 a2 u2, and assuming that it's an incompressible fluid, then we can put the equation this way. Of course, here we put the area as pi over 4 d square if it's a circular pipe. So pi over 4 will cancel out, the density will cancel out, so we'll end up with d square u1, d1 square u1 equals d2 square u2. And we can get a relation between u1 and u2 in terms of the diameters, which we should know. We should know that the diameters of the pipe itself and the obstructed area. And from this we can call or put d2 over d1 as beta, and of course beta is smaller than 1, and we can combine the equations, the continuity equation and Bernoulli equation, and with some simplification we can reach this conclusion that we can find the velocity u2 as 2 delta p over rho 1 minus beta square. So all the terms here are terms that we know. We know the values of, or we can measure, like delta p, or we know beta and rho. So we can know the velocity. And this is the general equation for all obstruction methods. It's not something that is different from any obstruction method than the other. But again, we are interested in calculating the flow rate. So now this equation is the velocity. So if we need the flow rate, then we calculate the flow rate using this equation, which is C du2 times A naught. Let's go back to the previous slide. This is the area at at u1, and this is the area at u2. Okay, so When used U2, we are using A node. A node is the area at the obstruction or the cross-section area of the obstruction. So we could, you should expect that the volumetric flow rate is U2 times A node. But what we have here is U2 times A node multiplied by CD. This CD it's called the coefficient of discharge. And this coefficient of discharge is it's smaller than 1. It's not larger than 1. This is a mistake. It's smaller than 1. We get the CD experimentally, and this is to account for the assumption that was not correct, which is that there are no losses. So definitely there will be losses. You have a fluid that is going through minor losses, like what we discussed before. It's changing the cross-sectional area, and as we will see in the shapes of the obstruction methods or the different flow meters, there might be a sudden change in the cross-sectional area. So this leads to a huge pressure drop or losses, huge losses. We use this coefficient of discharge to account for these losses that we didn't account for in the original equation. So we have these equations that we can use to get the coefficient of discharge. This is for orifice meter. Orifice meter is going to be around 0.6, around 0.6 plus or minus. But of course, this will give us the most accurate coefficient of discharge. Or for the nozzle, it's smaller. I mean, it's smaller losses, so it has higher coefficient of discharge. It's going to be more than 90%. Okay, so these are the three types. This is the orifice. So the orifice is just a disc. And you can imagine a flow going from a big area through this disc, from this area through the disc suddenly, and this is going to cause a lot of losses. The nozzle is making it more smooth, for the flow to be more smooth. So it's also like reducing the cross-section area, but it's gradually reducing the area. This agrees with what we mentioned before about the when we were discussing the minor losses, the sharp edges and the rounded edges. So it's the same thing. So we have here higher coefficient of discharge than in the orifice, and for the Venturi meter, it's the most smooth one of them. It reduces the area gradually, and it increases it gradually. So is even a better coefficient of discharge. One more, by the way, one more thing that I didn't mention before about the coefficient of discharge. In the Venturi meter, we are measuring the pressure drop actually at this area and this area. Okay, so when we say CD A node times U2, this is the actual area that we are measuring. In this nozzle, we are not measuring the velocity at the actual cross-section area. We are measuring it a little bit after this. And this is what we mentioned before as well about the vena contracta, about the entrance region. So we have also a vena contracta here. So this area is smaller than. So when we use A node, we actually have an area here that's smaller than A node, and the same here. The area is smaller than A node. So this is also accounted for using the coefficient of discharge. So anyway, and this is the idea, the basic idea of the coefficient or the obstruction method. We will solve an example or two in the next video, inshallah, to clarify this more. And I'll see you then, inshallah. Goodbye.